So welcome to the Friday Big Talk. And so today's lecture is in two parts. And so the first part is by Aaron Chen, and the second part is by Catherine Lee. And so first, I, Aaron Chen, will be giving my lecture. So yeah. So first of all, can everyone see the screen that I am about to share? So here. Can everyone see the screen? Okay. All right, got it. Yeah. So, yeah. So the first part of my talk today will be on Fermat's little theorem. So Fermat's little theorem. So first of all, what does it state? So Fermat's little theorem, what it states is that basically a to the p minus a is a multiple of p for if p is a prime number. So yes, equivalently in the modulus form, this would be a to the power of p is congruent to a mod p using mod form. So if a is not divisible by p, which basically means that a is not 0 mod p, then what you get is that a, you get the result that a to the power of p minus 1 is congruent to 1 mod p. And I think you can see how this is done because all you're really doing is dividing both sides by a. And so now let's move on to the first problem. So I'll give you a minute or so to try this on your own before I'll go over it. Okay, so I'll start going over this problem now. So we want to find the greatest common divisor of the elements of the set such that n of 13 minus n such that n is an integer. So first of all, we can just let this greatest common divisor be some variable d. So by Fermat's Little theorem, what you get is you can use the fact that n to the 13 is equal to n to the 6 squared times n is equal to n cubed to the 4th times n. And of course, mod, you can do mod 2. Then this all disappears to just n to the 4th because n squared and n cubed and n are both 1. And so what you get is that this is just congruent to n squared, which is congruent to n the mod 2. So 2 divides and then 13 minus n. And so next, another similar thing we can do is in the fact that 13 is n to the 4th to the power of 3 times n. And so this in turn tells us that 3 divides n to the 13 minus n. Oh, the notation I'm using here is this, which means that A divides B, or that B is a multiple of A. So now you can do this for a lot more stuff. So I won't explicitly go into how you do it. So in n to 13 minus n also works for 5. It also works for 7. And of course 13 also works. And so these are all prime numbers. So they're products of these 5 numbers, which is 2730 divided d. But now we have that to the power of 13 minus 2 is equal to, if you calculate this out, it's 8,190, which happens to be 3 times 2,730. But then 3 to the power of 13 minus 3, which is 3 times 3 to the power of 12 minus 1, is not divisible by 9. Then this has a 3, and this also is divisible by 3. That means that one of these 3's is not in the GCD. And so that means that 2,730 is the maximum possible value of the GCD. And we also already know that 2,730 divides the GCD. So our answer is just 2,730. So if you have any questions, please ask. And if not, we can move on to the next question, where I'll once again give a minute or so to try it on your own. Okay, so I'll start going over this problem now. So you want to find the number of non-negative integers less than 2019 that are not solutions to this expression. So first of all, we know that x is solution if x mod 7 is. And that's because this whole thing is just in terms of mod 7. So then one of the ways to do this is you can literally just test x equals 0, 1, 2, all the way to 6. And this is a method that does work. And so the topic for that I'm doing this lecture on is Fermat's Little theorem for now. It will expand to a more generalized theorem later, but that's not the point. So for now, I will be presenting the solution that uses Fermat's Little theorem. So x to the 8 plus 4x to the 6 minus x squared plus 3 is equal to is equivalent to x to the 8th plus 4x to the 6th minus x squared minus 4. And now you can see a pretty pattern here, which means that this is equal to x to the 6 minus 1 times x squared plus 4, all mod 7. And now 7 is prime. 1, 2, 3, 4, 5, and 6 all satisfy the fact that x to the 6 minus 1 is congruent to 0. So the only numbers that are not solutions are multiples of 7. So we want the number of non-negative integers, which means 0 is included. And so yeah, the 0 is not included. Sorry, 0 is not a solution, so it is included. So this results in one value. And the rest of the values is the floor of the 2019 over 7, which is 288 if you divide it out. And so the sum of these two values is 289, which is our final solution. So does anyone have any questions regarding this problem? And in the meantime, I guess there are none. So I'll move on to the second part of today, which is about Euler's totient function. So the totient function. So the limitation of Fermat's Little theorem is that it only applies when the modulus is prime. But now we have Euler's. We will now start introducing Euler's totient theorem, and we'll first introduce his totient function. So the phi function or the totient function both are equally acceptable. So this value is equal to the number of positive integers less than or equal to n that are relatively prime to n. So for example, phi of 6 is equal to 2, as it's just 1 and 5. Phi of 2 is equal to 1, because it's just 1. And by convention, I believe phi of 1 is defined to be 1 as well. So yeah. Sorry. So yeah. And so with that said, let's move on to the first problem that uses Euler's totient function. We're not using his totient theorem yet because I haven't introduced it, but we will be using his totient function. And so I'll give all of you a minute or so to try to figure this out on your own. Okay, so I'll start explaining this problem now. So we'll find the total number of rational numbers from 0 to 1, such that when r is written as a fraction in lowest terms, the numerator and denominator add up to 100. Sorry, 1000. Okay, so this is obviously from 4999 to 499 over 501. And so this is, we want to find the number such that n over m is irreducible. So first of all, we can see that n over m is equal to 1000 minus m over m, which, okay, which is equal to 1000 over m minus 1. So that means we want 1000 over m to be irreducible. So basically, as long as m 2 or 5 does not divide m, we should be good. And so I want to find the number that are not divisible by 2 or 5. And so, yeah. So next, so we are using the Euler's tangent function solution here. And so that means that although there is an easier solution that would involve something like 1000 over 2 plus 1000 over 5 minus 1000 over 1000 over 10, and then you divide it by 2. And we will not be doing the solution here. And besides, it's not 1000 that's the easiest time. But anyways, regardless of the point here is that Euler's tensor function can be used to give a different solution. And so, anyways, so the number of answers here is, we will first start off by using the function of 1000, which is 400. And so this means that there are 400 numbers relatively prime to 1000. But we want the number from 501 to 999. And so we can just directly have this, and it's 200. And the reason this works is because the halfway point of 1000 is 500, which is also divisible by 2 and 5. And so that kind of just works out well. And yeah. So now I'll be going on to explain Euler's tangent theorem. So let's find the Euler's tangent function. Then a to the power of phi of m is congruent to 1 mod m for any m, as long as relatively prime to a. Okay, so I don't seem to have much time left, so I will skip one of these problems, and I'll move on to, yeah, this problem. So, yeah. Okay, so I'll give a quick minute for you to try this on your own, and then I will just quickly run through the solution and then hand it over to Catherine. Okay, so this is going to be the last problem. And so I'll start explaining it now. So let f of n be the remainder when n to the n to the n is divided by 23 for each positive integer n. So I want to find the smallest positive integer k such that f of n plus k is equal to f of n for all integers, positive integers n. So you can see that phi of 23 is equal to 22, and conveniently phi of 22 is 10. And so if LCM of 23, 22, and 10, which is 2,530, divides this number k, then f of n plus k equals f of n is always true. And so this is fairly clear, as this part is used here, is used to take the modulus up here, and this part is used to take the modulus of this whole thing, where you're treating these two exponents up here as a single modulus using the first number. It's kind of weird to explain, but anyways, that's basically about how it works. And so we can see that 2,530 always divides k. And so now what we want to do is show that there is nothing smaller that works. So 2,530 is the smallest value. So we can let n be 0 mod 23. So then k is equal to 0 mod 23 as well. So the n plus k is always congruent to n. And so now if we let n be some number such that n to the 23 is congruent to n, and and it goes through all possible residues mod 23. So what this means, so there's a mathematical term for this. It's called n is a generator, but it's quite simple. And what it means is basically, so a generator mod 7 will be something like, I believe, no, nothing. I believe 4 is one. I cannot remember well though. So anyways, it's not. Okay. Then 5. So basically generator is something that goes like, it's basically something that's anyway, so basically it's just something, sorry. It's basically just something that loops through the list of all possible remainders mod p, or sorry, mod m, where except for 0. So in the case of any prime, or any prime p, there exists a generator. For sure. And so basically, this just guarantees that n plus k to the power of n plus k is congruent to n to the n mod 22. So now the choice of n here doesn't matter of the n mod 23, because the GCD of 22, 23 is equal to 1. So 22 divides k as well. And here we already had that 23 divides k. And so since n plus k is congruent to n mod I'm going to n mod. Okay, it's going to n mod 11. Then you use an exponents and the fact that 511 equals 10. Then we can make n a generator mod 11. And so that's n is congruent to n plus k mod 10. Okay, and so that means that 10 divides k as well. And so overall, that should mean that 2,530 divides k. And so this was from the bottom up, and our initial number here was this initial number, this number limited the bottom, and this number limited the top, and both of them reach 2,530. That means our answer is 2,530. And so finally, here is a homework question. So yeah, if you want, you can look at this problem. And so yeah. And so it's fine if you haven't recorded it down because this will be posted later in the YA Discord channel. And with that, thank you for listening. And yeah. And next we will have Catherine go next.